Sorry, this is 8.3. 8.2 was last time. Geometric sequences. So a geometric sequence is one where we multiply a term by a number to get the next term. So with arithmetic sequences, we added. With geometric sequences, we multiply. Same idea, similar process, but we multiply. So what we're saying is a sub n equals a sub n minus 1, the previous term, times some number, r. And we call r the common ratio. And the reason we call it the common ratio is if I divide both sides of this equation by a sub n minus 1, we get r, the common ratio. So we divide a term by the previous term, we get the same number every time. Just like with arithmetic sequences, if we subtracted, we got the same number. We had a common difference. So easy definition makes geometric sequences easy to work with. So you might be asked, determine if this sequence is geometric, is this sequence arithmetic, geometric, or neither. So what we want to do is decide, are we adding, are we multiplying, are we doing something else? So let's look at a couple of examples. How about 3, 6, 12, 24, dot, dot, dot. Is that geometric? Yeah. And what's our common ratio? 2. 2, yeah. How about 1, 1/2, 1/4, 1/8, dot, dot, dot. Geometric? Yeah? What's our common ratio? R equals 1/2 or 0.5. Multiply each term by 1/2 and we get the next term. This kind of geometric sequence, there's something special that happens with that. We'll talk about that in a little bit. Well, because our definition, the way that we get our terms, because it's nice, because it's easy, we're multiplying, we can find a formula for the nth term easily. And we're going to do it like we did with our arithmetic sequence. We can figure it out. We can figure it out on our own. A sub 1 is just a sub 1. A sub 2. To get the next term, we multiply a sub 1 by r. To get the third term, we multiply the second term by r, a sub 1 r squared. A sub 4, we multiply this term by r to get the next term, a sub 1 r cubed. So do we see the pattern? A sub n, dot, 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 is going to be a sub 1 times r to the n minus 1. And there's our nth term formula. Very, very similar to our nth term formula for our arithmetic sequences. But we're multiplying instead of adding. So, let's look at a couple of examples here. Let's find the nth term. We have a geometric sequence. And our first term is 5, and r equals 2. Well, for this one, we just have to plug in. So we get a sub n is 5 times 2 to the n minus 1. And I want to point out something here so we avoid a easy mistake to make. This is not 10 to the n minus 1. So don't do that. Because exponents come before multiplication in the order of operations. So you have to do the exponents first before you multiply. So don't make this mistake. Since we're dealing with exponents here, this would have to be like an exponential number of kittens or puppies got harmed there. Let's find the 20th term of that sequence. So we need to decide to find our 20th term. Is it arithmetic? Is it geometric? Or is there some other rule that we have to figure out? So what do we think? Geometric? Geometric, r equals 3. So we know that a sub 1 is 1. So a sub 20 is 1 times 3 to the 19th, which is 162, 261, 467. Very big number. Geometric sequences grow very quickly. It's part of what makes them useful as they model things that grow quickly. Population is geometric growth. Radioactive decay can be thought of as geometric growth. So it models a lot of natural phenomena. But it gets big very quickly. All right, questions? All right, so again, very similar to arithmetic sequences. We can come up with an nth term formula. We can come up with our next term easily. We can also come up with a method for finding the sum of a geometric sequence. When we deal with sequences, we want to find the terms. We want to be able to find a particular term, and we want to see if we can find a sum. So first we're going to talk about a finite geometric sequence. Thank you. And then once we come up with our formula, we will be able to find, in certain cases, the sum of an infinite geometric sequence. All right, so we're going to use a technique, a trick, not a trick, a method to find the sum, similar to what we did with arithmetic sequences. So S sub n, if we want an nth partial sum, we're going to add together a bunch of terms. Well, this is going to be a1 plus the next term, a1r, plus the next term, a1 r squared, plus a1 r to the third, plus dot dot dot, and we go all the way out to a1 r to the n minus 1. So that's our nth term. What we're going to do today, instead of writing this in reverse, we're going to multiply this by r. And I'm going to shift a little bit. So when I multiply a1 by r, I get a1r. When I multiply a1r by r, I get a1 r squared plus a1 r to the third plus, and I'm going to be able to match all of these up. The one before this, the previous term to a1r to the n minus 1 would be a1r to the n minus 2. And when I multiply that by r, I get dot 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 plus a1r to the n minus 1. And finally, when I multiply a1r to the n minus 1 by r, I get plus a1r to the n. So the one before this is a1r to the n minus 2. Multiply that by r, add 1 to the exponent, I get this. And when I multiply this by r, I add 1 to the exponent, and I get this. So we've matched up all of these in between. So now what I'm going to do is subtract these two equations. So s sub n minus r s sub n, because when I subtract, all of these are going to go away. That's going to go away all the way, except for that first one and that last one. So I get a1 minus, because I have a 0 minus a1 r to the n. And now we're going to factor. On the left-hand side, we'll factor out that common s sub n. And we get a 1 minus r. And I'm going to factor out the common a1. 1 minus r to the n. So finally, I can divide by 1 minus r, and I get my sum of n terms is a1, 1 minus r to the n, over 1 minus r. And that's my sum of a finite geometric sequence. I just need to know a1, and I need to know r, and I need to know how many terms I'm adding. That's a nice little trick there. Nice technique. All right, so let's look at an example of using this formula, and then we will talk about an infinite geometric sequence. So this is the sum of n terms, just for terminology, or the nth partial sum. Sum of n terms, nth partial sum, some kind of terminology like that. All right, so let's take a look at a couple of examples. We want the sum, n equals 1 to 20, of 2 times 0.1 to the n. So when we're looking at a sum, if the problem doesn't tell us if it's arithmetic or geometric, we need to decide, is it arithmetic, geometric, or is it something else where I'd have to do a lot of work and calculate 20 terms and add them all together. So let's write out some terms. A1 equals 0.1 times 2. And I'm going to write it like this, 2 times 0.1 to the first power. A sub 2 is 2 times 0.1 squared. A sub 3 is 2 times 0.1 to the third. Is this geometric? Are we multiplying each term by something to get the next term? Yeah, what are we multiplying by? What do we multiply 2 times 0.1 to get 2 times 0.1 squared? 0.1. We're multiplying by 0.1. So R equals 0.1. A sub 1 we decided is, I'll write it this way, 0.2 if we multiply that out. And we're adding 20 terms. So S sub 20, sum of 20 terms, this 20th partial sum is going to be 0.2 times 1 minus 0.1 to the 10th power, sorry, 20th power, we're adding 20 terms, over 1 minus 0.1. You can plug it in, you plug it into your calculator and calculate, that's fine. I just want to let you know your book, what your book does. They do everything in terms of fractions. So what they would do is write this as 2/10 minus 1 minus 1/10 to the 20th over 1 minus 1/10. And they would do this subtraction. They would do 10 to the 20th as a fraction. Do the subtraction, find a common denominator, and you'll see the answer in your book. They would give the answer as 2/9. Well, you could calculate it out, and you should get whatever 2/9 as a decimal is. All right, so that's a sum of 20 terms, the 20th partial sum, something like that. All right, we good there? All right, let's look at now an infinite geometric sequence. And usually when we start adding terms together, we call it a series. Our book doesn't use series until we talk about an infinite sum. So I'm going to say sum of an infinite geometric series. Usually series means we're adding the terms of a sequence. All right, so we said that our sum, our nth partial sum, the formula we came up with was a1 times 1 minus r to the n over 1 minus r. And we saw that if r was, for example, the problem we did, r was 3, geometric sequences grow very quickly. So if we added a bunch of terms, we should expect something very large. But if the absolute value of r is less than 1, so we have some fraction between 0 and 1, 1/2, 1/4, negative 1/2, negative 1/4, something like that. As n gets very big, what happens to r to the n? So let's think of 1/2. 1/2 to a really big power. Does it get bigger or smaller? Smaller. 1/2 to the 100 is really small. 1 over 2 to the 100. That's going to be really small. So as n gets very big, r to the n gets very small. As n approaches infinity, how small is r to the n going to get? What's it going to get close to? It's going to get close to 0. If we go 1 over a really, really huge number, we get a really, really, really tiny number. As n gets close to infinity, r to the n gets close to 0. So, I'm going to write this over here. The sum from n equals 1 to infinity of a1 r to the n minus 1 equals, well, in this formula, we have a1, 1 minus 0 as n gets close to infinity. 1 minus 0 is just 1. So we have a1 in the numerator over 1 minus r. And this would be the sum of our infinite geometric series. having trouble spelling. Finite. Infinite. Okay. And this is if the absolute value of r is less than 1. So some fraction between 0 and 1. So even though we're adding up an infinite number of terms, because they keep getting smaller and smaller and smaller, we get a finite sum. So we saw the example a couple of days ago. We went 1/10 to the n power. We decided that was 0.1 repeating, finite number. So let's look at an example. The sum n equals 1 to infinity of 2 times 0.4 to the n minus 1. Is this geometric? Yeah, we multiply each term by 0.4 to get to the next term. So r is 0.4. A1, 2 times 0.4 to the 1 minus 1, 0.4 to the 0 power. What's 0.4 to the 0 power? Anything to the 0 power? 1. So it's 2 times 1. So A1 is 2. So this is going to equal 2 over 1 minus, I'm going to write this as 4/10. So this is 2 over 10/10 minus 4/10. 2 over 6/10, which is 10/3. 26 or 10/3. So that sum would be 10/3. 3.33333. Questions? It's really amazing how different this class is from my 6th period class. It's just, yeah. They're very noisy. All right, I want to introduce, before I give the homework, I want to introduce a topic that will, or not a topic, one piece of information that we will use, or we will be able to use if we want, on Friday when we talk about the binomial theorem. And it's something we might know about already. Pascal's triangle. So Pascal's triangle, we start with ones. And we always have a 1 on the outside. And we get the number below here by adding these two above together. So 1 on the outside, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. I'll do one more. And we can keep going. So for what we're going to do on Friday, I'm going to call this, we'll label these by rows, and we call this the 0th row. So this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, etc. So we start with the 0th row. Pascal's triangle has some very, not some, it has a lot of very interesting properties. So one of them, we'll use one that I don't talk about today, but we'll see it come out when we talk about the binomial theorem. One of them is if we add the numbers in the row. So if I add all the numbers in the first row, I get 1. If I add the numbers in the second row, 1 plus 1, I get 2. Here I get 1 plus 2 is 3. I get 4. Here I get 6 plus 2, I get 8. Here I get 10, 14, 15, 16. Here I get 20, 32. Well, this is 2 to the 0. This is 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. So this is n equals 5. If I keep going, not 25, 2 to the fifth. If I keep going, dot, 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 if we add all the numbers in the nth row, we get 2 to the n. So the sums of the numbers in the rows of Pascal's triangle are powers of 2. The Fibonacci sequence is also in Pascal's triangle. If I do something that we call the shallow diagonals, put an arrow on here, and I'm going to add the numbers in the shallow diagonals. 1. 1. 2. 3. 5. 8. Etc. So if we add the numbers in the shallow diagonals, we get the Fibonacci sequence. The Fibonacci sequence and Pascal's triangle, they're very interrelated. There's lots of stuff with those two things together. So mathematically, Pascal's triangle is extremely well studied mathematical object. It's really, there's a lot of stuff hidden in there. So that's just a couple. We'll look at something else that's in Pascal's triangle in not quite as subtle a way when we talk about the binomial theorem tomorrow. So I just wanted to introduce the idea and how we construct it, or reintroduce the idea if we've seen it before and how we construct it. So when we talk about it tomorrow, we can just say Pascal's triangle. All right. Thank you. All right, there we go.